Hi, welcome to the Semantics lecture about formalizing definiteness. Now, definiteness we've seen truth conditionally, we'll see it compositionally, and in this lecture we're going to focus on how we turn those truth conditions into something formal. And the way that we do that is by taking not just the truth conditions, but different elements of the meaning and bringing them together, using them in different ways to really get the most out of each part, and then we use those to build a formal meaning. So we've seen how the truth conditional meaning of definiteness involves reference and a presupposition of uniqueness. And we know that the syntactic structure of the determiner phrase is built a certain way. And we have our theory of syntactic types, semantic types. There's no such thing as syntactic types. So we have truth conditions, syntax, and semantic types. And using those three things, those three elements, we can build our formal meaning. Now for the syntax, we just employ the DP hypothesis. And it's widely accepted in syntactic theory, although for our purposes here it actually doesn't make too much of a difference. But we need to have some idea of what the syntax looks like, and this is as good as any other. And in many syntactic ways it is superior. So once we have that, we have the determiner, and it takes the noun phrase as its complement. Then we have our theory of types. And so the theory of types allows us to classify different expressions by the sorts of semantic objects that they denote. And our noun is professor, right? So we have professor. And we know what its type is. It's a function from individuals to truth values, so it's of type ET. We can see that in 2, and that's our denotation for it. Now if we build a meaning tree based off of the LF in 1b, we see that we have the types of all of the nodes but one. The professor is of type ET, and the DP, the professor, is of type E, that is to say, it refers to a particular individual. And of course we can plug it into a verb phrase of type ET and get a sentence. So when we have any situation where we have 3 nodes and we know the type of 2 of the nodes, then we can figure out the type of the third. And it doesn't matter if we know these 2, or these 2, or these 2, right? If there's one missing, we can use the other 2 to figure out what the type of the third node needs to be, and that's going to help us shape its formal denotation. Doesn't say it's recording. So we can use a logical argument to figure out what the type of the and professor is. The and professor are sisters, so they're going to combine by functional application. We know that that means plugging one into the other. Now the semantic type of any function is going to be the ordered pair consisting of the type of its input followed by the type of its output. So the type of the input here is E and the type of the output is T. However, the mother of this node is of type E, which means that this cannot be the output of this. Well, if this can't be the output of this, this cannot be the output of this, but these have to combine as a function and argument, then this can't be the function. Ergo, it must be the argument. So this has to be a function. And what is its function? Well, it's a type, its output is of type E, and its input will have to be of type ET. So this function will have to be of type ET, E. That's got to be the type for the. And so in 4 we have type ETE. And what does it mean to be of type ETE? Well, it means that you're a function, and it means that you're a function from the set of things of type ET to the set of things of type E. That is to say, it's a function from properties of individuals to the set of individuals. So it links a property to an individual. So we've determined the kind of semantic object that we need the to be. It's a function from properties to individuals. Now we can use the truth conditions that we discussed in order to figure out how we link the property to that individual. Recall that we found that the involves reference, and a presupposition of existence, and presupposition of uniqueness in a context. And so the professor, in the context we're talking about, is essentially me. Its denotation is me, which is the same as the denotation of my name. So if I say the professor knows semantics, right, that's going to be true anytime Andrew Mackenzie knows semantics is true, and false anytime that the other one's false. So if we take the, then we can characterize it as something that takes a property, a set of individuals, and it finds and it picks out, right? It localizes the only one with a given property. And so we get a sense that you feed it a property, it gives you the individual with that property, and now we just need to understand how do we encapsulate that intuition into a formal meaning. So how do we turn a meaning into something formalized? Well, we need to know what kind of semantic object we're dealing with, and we need to know what the truth conditions of that meaning are. And when I say a kind of semantic object, I'm referring to our ontology, the list of kinds of semantic objects that we have. And we have individuals of type E, truth values of type T, and so far we have properties of type ET. So our semantic object needs to be in there somewhere. Now, we use the structure in the type theory to figure out what kind of semantic object the needs to be. It's not on this list, right? It's of type ETE. So it takes, it's a function then from the set of things of type ET to the set of things of type E. And we can see that on the top of page 4. So we have this function notation, and we're just going to fill it in one piece at a time. Right? We know its type, so now we know its domain, and we know its range. So the sorts of objects in this domain that are of type ET are themselves functions. So when we're adding them to this formal definition, we can use a variable to represent them. Usually we use f, but f is taken, as you can see, so we'll use g. So now we can plug in for any g in d sub e, t. Then f of g will equal some meaning. What is this meaning? Well, that's the second part. Right? Now we know what the formal object is. Now we just need to add the actual truth conditions. And we know that it involves reference and it involves a presupposition. And how do we formalize that? Well, presuppositions are propositions that another proposition depends on, right? So our expression can only mean something if the presupposition is true. So how do we encode that only if relation? Well, you can think of several ways to do this, but what we're going to do involves what's called domain restriction. That is to say, we're going to limit the domain. So instead of saying any function from in d sub et, we're only going to pick out particular ones, the ones where the presupposition is met. Why? Well, remember that when presuppositions fail, the expression is neither true nor false. It doesn't mean anything. That is to say, it's uninterpretable. Well, if we have a function and you try to pick something that's not in its domain, you won't get anything in the range. So it's going to not give you a result, and so it will be uninterpretable. So we can use domain restriction to bring about uninterpretability in a function. So how do we restrict the domain in that sense? Well, we have this presupposition of uniqueness, which entails the presupposition of existence. And we have this concept of reference, and we'll get to the reference part. But the presupposition of uniqueness is pretty straightforward, right? There is only one individual in d sub e that has this property. So in the case of professor, there's only one professor. But wait a second. we talked about this, where there's more than one professor in the world. So we can't just say the unique professor on Earth. We have to limit ourselves to some context. And the way that we can do that, well, there's a lot of ways we can do that actually. But the way that we're going to do that, that fits with what we've been doing so far, is to say that when we use the, instead of saying d sub e, we're going to just select a subset of d sub e that will be the right size. So if we're talking about a classroom, and I want to say the professor, I don't need to pick all of d sub e. I just need enough people, the set of people in the classroom. And we can call that c sub e, c for context. So we can let c sub e be a contextually salient subset of d sub e. Now, armed with c sub e, we can write our presuppositions. Existence, there is an x in c sub e with the property, and uniqueness, there is only one. And now we can add these as a domain restriction. And we can do that by putting it over here. Right, so for all, or for any g in d sub et, such that there's only one individual in c sub e where g of x equals 1. That is to say, there's only one individual in the contextually salient subset of individuals that has this property. So we're only picking properties in d sub et that are met by one person in our context. If a property is met by more than one person, it doesn't get picked. If a property is met by 0 people, it doesn't get picked. Right. So in that sense, we are now limited to the properties that have one person satisfying it. And so we have our domain, we have our object, we have our presupposition. What does it mean? What is the output? Right? Something of type E. What is that thing? Well, it's the unique thing that has that property. It is the reference, the individual. And we can put that in our meaning like this. So now we have the means the function from the set of properties to the set of individuals, such that for any property that is held by one individual in the context, f of g is that individual, the unique individual, such that g of x equals 1. Right? And so now we know what the means. The meaning of the, in English at least, is very straightforward. It denotes the partial function from properties to individuals such that for any property where there is only one individual in the salient context with that property, the function returns the unique individual in the salient context with that property. And for all other properties, it's undefined. It's pretty easy, right? You all figured it out when you were children. So it's not very complicated. Sort of, right? They say English isn't hard. Now, we have this meaning for the. Right? And now I want to say, well, how do we turn that into a lambda expression? Because I don't want to have to write all that every time. So we have our function, we can convert it to a lambda expression using the same techniques we used before. So let's review that technique real quick. So we have our function, domain and range, and for any object in the domain, f of a function applied to the object is some meaning. And so we take the object in the domain, we make the lambda expression out of it, and then the meaning is the value condition. And so we get that intent. Now of course we were writing the value conditions a little bit differently in an abbreviated form, and we get the result in 11. Now we can do that with the, and it's the same result. So we take the object, the domain, and the meaning. Now the presupposition, there is a way you can add it. We're going to leave it off to the side. And we get what we get in 12. So we get lambda g in d sub et, the unique x in c sub e such that g of x equals 1. And of course that's a lot to write as well. And we usually employ an abbreviation of this. It's called the iota operator. It's called iota because you get this squiggly little eye looking thing, which is the Greek letter iota. And we put it in front of the variable instead of lambda. And iota gets us the unique variable thing such that g of variable equals 1. So in 13 we get the meaning of the iota operator. And so we can replace 13 with 14. So we have the, meaning the lambda g in d sub et, iota x in c sub e, g of x. And that's of type ete. And once we have that, we can plug it in to our compositions, and we can do anything we want with it that we do with other expressions. Alright, so to summarize, we've seen that we have the syntax, the type theory, and the truth conditions, and we bring them all together, and we employ bits of one and bits of the other, and we mix them all together. And we proceed in a very straightforward fashion, building on the parts that we know to formalize the parts that we don't know. We figured out what kind of formal expression the needs to be, converted that into an actual function, and then added the truth conditions and presuppositions in a way to make the function complete and whole. And so, what we learned then is how to formalize a meaning, and we can apply this solution to pretty much any kind of meaning we encounter, and we'll want to be doing that. And so, in addition, this formalization allows us to make precise predictions about what the means, when the can mean it, and about what kinds of solutions we can imagine to handle cases where the meaning of definiteness is present, but the is not.